Okay, for the last lecture, we are going to be talking about how to measure the volatility of a portfolio. Again, for those of you studying finance, this won't be new. So, first of all, to remind us what volatility actually is, it's a rather approximate measure of by how much a price could change 1 year from now. It's quoted in the annualized terms. Even if you measure it over a short period, you're going to compound it up to be 1 year. For instance, if you say the volatility is 25%, it means very roughly that this time next year, there's about, so assuming a normal distribution, so 25% is like 1 standard deviation. So 68% chance that within a normal distribution, it's going to be plus or minus 1 standard deviation. In other words, so if you say there's 25% volatility, then there's about 68% chance that the price could be 25% higher or lower than that. So volatility is really based on a standard deviation, but it's just annualized. So to find the standard deviation, first of all, we must compute the variance. And now I'm going to be talking about how to calculate the variance of a portfolio. Suppose you've got constant weights on a portfolio. So the variance sigma squared P of a portfolio P uses the portfolio weights, not the holdings, and the standard deviations and correlations, or covariances, if you like, of the assets returns. So we can express it in 2 ways. With the covariances, it's going to be the sum of the squared weights times squared standard deviations. In other words, the squared weights times the variances, plus 2 times the sum of the weighted covariances. And this goes back to, remember the end of statistics? We did this. So it's rule 3. That rule is what I'm using here for the portfolio volatility. But because the covariance is just the correlation times the product of the standard deviations. I mean, we saw that formula before, but it was actually presented as correlation is covariance divided by the product of the standard deviations. But we can turn it around and do it like this. So if we like, we can just substitute in the formula above. Instead of the covariance, we can have correlation times the product of the standard deviations. But this formula is pretty horrible. And that's one of the reasons, in fact, the main reason why, when n is large, writing out all those things becomes very, very difficult, and it's much easier to do it in matrix notation. Anyway, so let's just do it for a very simple example where we've just got 2 assets. One has volatility 20%, and the other has volatility 25%, and the correlation is 0.4. So you just need the 2 volatilities and the correlation. You don't need to know the covariance. Because you can get the covariance as the product of the correlation and the 2 volatilities. So let's find the volatility of a portfolio where 2 million is invested in one asset and 3 million in the other. So we have to find the weights. Remember here, the formula, the variance portfolio is going to assume the weights are constant. So the weights are 2 over 5 and 3 over 5. So that's 0.4 and 0.6. And then using that formula here with just n equals 2, it gives you the first weight squared times standard deviation squared, etc., etc. So that gives us the variance, and the volatility is just the square root of that because we were given the inputs in terms of volatility. We didn't have to compound them into like daily standard deviation into annualized standard deviation. Now, earlier in this topic, we looked at matrices, and you might have thought, well, what's the relevance of that? But the most important thing to take away from that is that we are using the sort of heart of a risk model is this covariance matrix of the returns on the assets. So if you've got n assets and returns R1 to Rn, and the covariance between R1 and R2 is the first, first row, second column. The covariance between R5 and R6 is the 5th row and the 6th column. those are the elements of the matrix. We call them Vij. The diagonal elements, the covariance between R1 and R1, or between R5 and R5, the covariance of X and X is just the variance of X. So the diagonal elements of this matrix are the variances. And also, every covariance matrix is symmetric because covariance between R2 and R6 is the same as the covariance between R6 and R2. It doesn't matter the order. So you've got a symmetric matrix where the variances are along the diagonal and the covariances are on the off diagonal. And important to note, every covariance matrix needs to be positive definite. That's because the variance of a portfolio can be written as a quadratic form. So we put in the weights as this, before we saw x prime ax. Now x is going to be the vector of portfolio weights and A is going to be the covariance matrix. And whatever the weights in the portfolio, we've always got to come up with a positive number for the variance of the portfolio. So let V be this covariance matrix, and W now for the weights. W prime VW is the variance of the portfolio return, assuming V is the covariance matrix of the returns. So even if weights are negative, because you could look at short positions as well using weights, so they could be negative. But whatever they are, the covariance matrix must be such that W prime VW is a positive number. So here's an example of a covariance matrix, and that's, if you spell it out with arbitrary weights, W1 and W2, it's going to be this quadratic form. Previously, we looked at that with X and Y, and now we're looking at it with weights W1 and W2. And in general, it doesn't just have to be for two. We've got this big covariance matrix. It can be like 400 in risk metrics. You know, you've got a 400 by 400 or more than that. These would be the variances of general risk factors on equities, bonds, commodities, and so forth. So the diagonal elements are the variances, and the off-diagonal elements are the covariance. And then using matrix multiplication, it could be shown that this formula that we saw previously for the variance of a portfolio, which itself was based on this statistical operator, this rule 3, gave us the formula here. We can see that this formula is actually, this formula is the same as the quadratic form, which is so much shorter and easier to write down. So, for example, this is the same example as we did before, but we just used the this formula here, but we've also done it just using this formula here. It's the same example, but here we have again the variance covariance matrix. These are the variances, these are the covariances, these are the weights, and then doing the matrix multiplication gives us the same answer as before. Okay, now we have to talk about annualization because that example gave us the input in terms of actual volatilities. But what if you've just got the daily standard deviation? How do you calculate the volatility? All right, so underneath all this, first of all, we have to remind ourselves of what it means for a stochastic process to be independent and identically distributed, in other words, IID. So you can think of a stochastic process whose realization would be a time series, and it would be a time series of returns, which looks a little bit like a hairy caterpillar. It goes up and down. Sometimes there's volatile periods and it goes up and down. Sometimes it's very tranquil. But each one of those observed returns is actually a realization on a random variable because in the previous period, we didn't know what it was. And did we have a large variance or a small variance? So a stochastic process is like a series of distributions of random variables. And we say it's IID, independent and identically distributed, if the distribution that governs the realizations of those returns is identical throughout the whole series. It's the same at every point in time. And also, it's not influenced by past values, so it's independent. And in particular, returns can't be autocorrelated. In other words, you can't, if you suddenly have a positive return, you're not going to get like positive autocorrelation, another positive and another positive, you know, that's positive autocorrelation in returns. Or negative, you know, if you have a large positive return, you're not suddenly going to have a large negative return because of that. The past returns have no effect on the return today. That's independent. Now, when we use the log approximation for realized returns, we use little r instead of capital R now for the log returns. The h-day log return, I'm going to call it rht at times t. So that's going to be the sum of the forward-looking daily returns, as in this formula. Now, if we apply, again, harping back to these rules, the expectation of the sum is the sum of the expectations, right? And the variance of the sum, the covariance is 0 because they're independent. When they're independent, the covariance is 0. Then the variance is just the sum of the, you have to put the coefficient squared now, but it's just the sum of the variances. So in this formula here, if you apply the expectation operator, we find that the expected return is just the same because they're identically distributed. So it's like mu plus mu plus mu. It's the same mu every time. So it's just like h times mu. And the variance is going to be the variance of the first one-day return plus the second one-day return. So it's just h times the variances as well. So the expectation is h times the one-day expectation because they're all identical. And the variance is just h times the one-day variance. But that means that the standard deviation is the square root of h times the standard deviation of the one-day log return. And that's what we call the square root of time rule. So when we want to annualize the volatility of a portfolio from daily or weekly or monthly or whatever it is into the volatility of the portfolio, then we need to use this square root of time rule. So if we assume there's 250 trading days a year, or it could be 365 for crypto markets, and if we use the square root of time rule, as we showed in the previous slide, if the log returns are IID, then mean and variance both scale with the holding period. So the mean and variance of annualized returns would be 250 times the daily return, the mean of the daily returns, or the variance of the daily returns. But then the standard deviation would be the square root of 250 times the standard deviation of the daily returns. So that's why we've got h as the scaling factor to get mu h, that's the mean of the h-day returns. It's h times that. And the standard deviation of the h-day returns is the square root of h times the daily standard deviation. So h could be 250, or it could be something else. We don't always scale to annualize, but typically that's what we do. So here's some examples. Find the volatility of an asset whose daily returns, we've got sigma 1 is 0.02. So for that, we need to use square root of 250 as the annualization factor, and we get 0.02 times square root of 250, which is 31.26%. What about if we've got monthly returns? The monthly standard deviation is 8%. Well, then the sigma 12, the monthly one is 0.08, but the annualization factor is 12 months, not 250 days. So we take the monthly standard deviation and multiply that by the square root of 12 to get sigma 250, which is the volatility. Here's another example. Find the standard deviation of the daily returns if the volatility is 20%. So now we have to scale down. So 20% volatility, which is 0.2, needs to be divided by the annualization factor of the square root of 250, which is 1.265. Here's another one. Find the standard deviation of 10-day returns for an asset with volatility of 20%. So that's a bit more complicated. How many 10 days are there in 250? 25. So we scale down by 25. Alternatively, you can scale down by 250 and scale up by 10, but the net result is the same. So finally, we're going to have a look at the Excel spreadsheet where we calculate the mean and variance in two equivalent ways. One is, and this is with constant weights, one is to take data on each asset return and multiply the current portfolio weights by each of the returns and use that formula that the return on the portfolio is W prime R. And it's going to be a time series. So each of the R in the vector is RIT. So it's going to be the return on portfolio at time T. And then we'll just get the reconstructed, they're not the actual, there's hypothetical historical portfolio returns, assuming that we always have the same weights as we have today. And then we just use equals average and equals var to get the mean and the variance of the time series. So we can do that. Or we can just use these formulae that the mean of the portfolio return is just the dot product between the weights and the mean of the portfolio returns, the vector of the asset returns, and then that quadratic formula that's going to be very important in this module. So we're going to have a look at the Excel spread workbook for that in a minute. There's another way to calculate historical data for portfolio volatility. So we can use historical data, applying the current portfolio weights to the asset returns on every single day. That gives you a time series of observations that are based on the assumption that the current weights were always the weights in the entire historical period, which means you rebalance the portfolio to constant weights every day. And then we just apply standard deviation and average and so forth to get the portfolio volatility and mean. Or we could use the variance of a time series of observations, that's the equals var calculations, and take the pairwise covariance between all pairs of assets in the portfolio and construct this covariance matrix and apply the formula. That's what we're going to do in this spreadsheet. But just to summarize, there are two equivalent ways we can apply the formula, and we can also use the calculations, the formula W prime R, or number two, we can apply the quadratic form, and they give us the same answer. All right, so now I'm just going to go to the spreadsheet. Here it is. So as I said, with all the spreadsheets that you get with this module, anything red can change, so we can change that to 50 if we like, and watch all the blue things change. Everything blue is an output, don't change that. And we can change that as well. You see everything changes. What doesn't change, as we see, is the mean and the variance and the covariance matrix. They're nothing to do with the holdings. These are the holdings, and they will affect so the number of shares times F934. That is the time that we're looking at this portfolio. It's the very last observation. If we scroll all the way down to row 934, we'll see the price of Amazon in cell F934. So the price of the holding on this date, which is the 23rd of September 2024, times the number of shares is the amount invested in Amazon. And similarly for Tesla, that's the amount invested in Tesla, and this is the portfolio value, just the sum of the two. And the weights are, for this one, 35.35% is 18/52. It's the price, the amount invested in Amazon divided by the portfolio value. So that's that here, and similarly for Tesla. Now, these quantities, these statistical quantities, the mean, which is just the average of the Amazon returns. Remember, we use ordinary returns, not log returns, because that formula that the expected return on the portfolio is the sum of the expected returns on the assets only applies to ordinary returns, not log returns. So here we've got the ordinary returns for Amazon and Tesla, and we've got the variance of these returns. That's the equal var command. And that's the mean, and this is the var, and the covariance. We've got the var, which is just the variance there, the variance there, and then we've got the covar command, which uses n-1, as I said, which makes it easier for computing correlations and other things. All right, so that's there. Now, what about the constant holding portfolio? So just assume we always have the same number of shares, even in 2020, as we did in September 2024. So then we just multiply the 100 times the Amazon price plus 150 times the Tesla price. Assuming, like I have, you just ignore your portfolio and you don't rebalance it at all, then this is the price because you haven't changed the holdings at all, no rebalancing. Okay, so now we're going to look at the portfolio returns two ways, assuming that holdings are constant. So here, we just look at the constant holding portfolio price and find the return on that. But for the constant weights, we apply the weight times the return plus the weight times the return. This works because it's not log returns. Okay, and then you fill down all of those. Now we can have a look at the mean and the volatility based on two things. First of all, constant holdings. That's just the average of the constant holding portfolio returns, and the volatility, which is the standard deviation of these returns times the square root of 250, because we use the square root of time rule to annualize. For the constant weights, we use this time series. That is the average. And remember, when we scale the daily returns to an annualized form, we don't use the square root. We multiply by 250, not the square root of 250, as explained in the slides. Okay, so you can see these are quite different, right? But the thing about using constant weights is that there are many different ways to calculate them. For example, here, we just use D2, which is this weight here, times the mean return plus D3 times the mean return, and then we use the 250 annualization factor. And here too. This is the formula for the variance, and the whole thing is in brackets. Look, we've got the square root of the weighted sum of the variances and the covariances, that blue bracket there, you can see here, it's the square root of all that times now the square root of 250. And this is the same formula, exactly the same, but it's based on W prime VW rather than the summation formula. And you think, why should we use this complex formula instead of the simple sum? Well, because here we've only got 2 assets. But suppose you've got 400 or 1,000. You can't code all that. You have to code this formula, which applies however many assets you've got. So I think we need to dive into this a little bit more using this Excel spreadsheet during the in-person lecture, probably. Bring some questions when you come. All right, so that's it for now. And next thing is topic 4.